In the last lesson, we saw that hydraulic systems use fluids to transmit energy. In this lesson, we are going to discuss the characteristics and applications of three kinds of hydraulic fluids. Petroleum-based fluids are the most common. They're made from refined petroleum. Usually, they're just called oils. Water-based fluids are often used where fire resistance is important. They are generally made from mixtures of water, oil, and other fluids. Synthetic fluids are often used as well. They have good lubricating ability and are highly fire resistant, but because they are not compatible with all systems, their use is often confined to special applications. In addition to transmitting hydraulic energy throughout the system, all three of these kinds of hydraulic fluids provide lubrication. That is, they reduce friction. Without proper lubrication, metal-to-metal contact, for example, between the vanes and the inner surface of this rotary pump, would cause the pump to heat up and wear out very fast. Fluids that lubricate systems properly will have two important characteristics: good lubricity and the correct viscosity. Lubricity refers to a liquid's ability to form a durable fluid film between surfaces. For example, petroleum oil has good lubricity. It forms a relatively thick film, and it adheres to a metal surface well. Water-based fluids, however, do not generally provide as much protection as oils or synthetics because they are not as thick, nor do they adhere as well as petroleum oils. The other characteristic of hydraulic fluids we need to consider is viscosity. Viscosity is a measure of the fluid's resistance to flow. The higher the viscosity, the thicker the fluid and the slower it flows. When thinking about viscosity, think how honey pours slowly when compared to a fluid like water. We say honey has a high viscosity because it takes a long time to pour, and water has a low viscosity because it takes less time to pour. Viscosity is often measured in Seybolt universal seconds, often called SUS or SSU. However, the International Standards Organization Centistoke measure, CST, is becoming more common. Viscosity in Seybolt seconds is measured by a meter, which times the rate at which hydraulic fluid flows through a precision-made hole at a specific temperature, usually 100 degrees Fahrenheit. If the fluid takes 150 seconds to pass through the hole, we say we have a 150 Seybolt universal seconds fluid at 100 degrees Fahrenheit. If we raise the temperature of oil, its viscosity decreases and it flows more easily. Pressure has the opposite effect on viscosity. As the pressure goes up, the viscosity of a liquid increases. Making sure a hydraulic system has fluids of the correct viscosity is important for two reasons. Components like this valve are built with very close tolerances between parts. Fluid with too high a viscosity could not get into the small clearances between moving parts to provide the proper lubrication. The lack of lubrication will cause excess wear and could lead to complete failure of the component. Viscosity is also important because the fluid helps reduce leaking between close-fitting parts. If the viscosity is too low, the component will pass too much fluid through these clearances and flow through the remainder of the system will be reduced. In addition, as the fluid passes through these narrow clearances, more heat will be created by friction. The change in a fluid's viscosity at different temperatures is referred to as its viscosity index. The higher a fluid's viscosity index, the less the fluid's thickness is affected by temperature changes. For example, the viscosity of a fluid with a high index may change from 150 SUS to 70 SUS as the temperature rises from 100 to 200 degrees Fahrenheit. But the viscosity of a fluid with a lower index might change from 150 SUS to just 40 SUS as the temperature rises from 100 degrees to 200 degrees. Most components of a hydraulic system are designed to operate within a relatively narrow range of fluid viscosities. It is essential that you always make certain the fluids you use match the specifications called for by the equipment manufacturers. As industry's use of hydraulics has expanded over the years, a variety of chemical additives have been developed to handle problems of excessive wear, extreme pressure, oxidation, foaming, and rusting. Several kinds of anti-wear additives are available. One common type works by increasing the lubricity of the fluid. The molecules in the additive form a film which helps to keep the surfaces apart. Unfortunately, this kind of additive has a limitation. It tends to break down at high temperatures. To overcome this limitation, another type of anti-wear additive actually bonds with the metal as friction heats up the surfaces. The bonded molecules smooth out the surfaces and reduce wear. There are also additives made for systems that operate at extreme pressures, typically above 3,000 pounds per square inch. When systems operate at such high pressures, any surfaces which actually touch attempt to weld together. However, the high heat at these points activates the additive in the oil and keeps the surfaces apart. Another common problem, especially with petroleum-based fluids, is oxidation. Oxidation occurs when oil combines with oxygen. This usually happens in the reservoir or at the pump outlet. In the reservoir, the surface of the oil reacts with oxygen in the air, forming mild acids and soaps. The acids can pit or corrode the metal surfaces of components, while the soaps can plug orifices and clog lubrication paths. Proper operation of many components, like this pressure control valve, for example, depends on a close fit. If acids corrode the metal surfaces, clearances like these will increase, and the system may not operate correctly. Heat speeds up the rate of oxidation in a reservoir very quickly. Generally, oil oxidizes twice as fast as normal for every 20-degree Fahrenheit rise above an average reservoir temperature of 130 degrees Fahrenheit. Oxidation inhibitors can be added to the oil to slow the oxidation process in the reservoir. However, oxidation inhibitors have little effect when oxidation occurs at the outlet side of a hydraulic pump. Oxidation in the pump happens when the air is allowed to enter the suction line through a leak or by excessive churning of the oil in the reservoir. In either case, the air forms bubbles which collapse when they are subjected to the high pressure at the pump outlet. This not only oxidizes the oil, but the collapsing bubbles create extremely high temperatures, which can actually fry the oil, forming resinous materials. The resins remain dissolved until they reach a hot metal surface, like a pump rotor or a valve. The hot surface will cause the resin to form a varnish that coats the metal surface. This varnish makes moving parts stick. The resinous material also forms a sludge that can plug up orifices and filters. Oxidized oil can often be detected by smell. It usually has a burnt odor. Oxidized oil can also be identified by rubbing some between the thumb and forefinger. It won't have the lubricity of new oil. Instead, it will feel more like water. If a fluid sample has either a burnt smell or feels too thin, and if a fluid analysis indicates that the fluid has been oxidized, you will have to drain and flush the system, clean the varnish deposits and sludge from components, and refill the system with fresh fluid. Another additive often found in petroleum fluids is an anti-foaming agent. This chemical additive helps control the creation of bubbles in the oil. In many reservoirs, baffles are used to prevent returning fluid from being sucked directly back up into the pump. This allows air to escape from the fluid before it is drawn back into the system. However, some reservoirs don't have baffles, and some systems churn the oil so much that baffles aren't enough to prevent foaming. You can check for foaming oil by taking a fluid sample near the pump inlet in the reservoir. The foam will be obvious. If it is present, check the system to find the source that is allowing air to be drawn into the system. Another common problem is rust. Rust may begin to form in a hydraulic system whenever water contaminates the fluid. Rusting is similar to corrosion in that it involves oxidation, but in this case, it's the metal parts of the system that are oxidized, not the hydraulic fluid. While corrosion removes material from metal surfaces, rusting adds material, and it often interferes with the operation of components. A buildup of rust on the inside surfaces of a valve, for example, may keep it from operating smoothly and can even prevent it from operating at all. Rust is usually formed when water condenses on exposed metal surfaces. Moisture-laden air is constantly drawn into the reservoir through the breather cap. When the system cools down, water vapor condenses out on the reservoir walls and eventually makes its way into the fluid. Even small amounts of water in petroleum-based hydraulic fluids, less than half of 1%, can start to rust the system. However, except in critical systems, this isn't usually reason enough to discard the oil. If the water content is 1% or more, the oil will look milky. Oil manufacturers often add a rust and oxidation inhibitor to the oil. The rust inhibitor coats the metal surfaces of the system with a chemical film and retards rusting. Petroleum-based fluids have become the fluid of choice in most industrial hydraulic systems. They provide good lubrication and they are relatively inexpensive to use. However, they can be a fire hazard. If the oil gets out of the system, it can encounter temperatures hot enough to cause it to ignite. In situations where fire is a potential hazard, fire-resistant fluids are often used. These fluids are either water-based or synthetic. Keep in mind, however, that none of these fluids is completely fireproof. If you get a fire-resistant fluid hot enough, it will burn. One common type of fire-resistant fluid is a mixture of water and oil. These are called emulsions because they also contain chemicals called emulsifiers, which keep the oil and water from separating. The two kinds of emulsions you're likely to find in use today are an oil and water combination called soluble oil fluids and various types of water in oil combinations called invert emulsions. A soluble oil fluid usually contains 90% water. Since water is a poor lubricant at the high pressures common in modern hydraulic systems, soluble oil fluids aren't as widely used as they once were. However, they are inexpensive, so you'll still see them used where the decision has been made to accept reduced component life in favor of an inexpensive fire-resistant fluid. When an emulsion has more oil than water, it's called an invert emulsion. They are usually no more than 40% water, which means they are less fire-resistant than soluble oils. But because they contain more oil than soluble oil fluids, they provide better lubrication. However, the oil and water in an invert emulsion tends to separate out easily, especially when the fluid is stored or used at low temperatures. Separation of the emulsion is easy to spot if you let a sample of the fluid rest for a time. Another problem with invert emulsion fluids is bacterial growth. To reduce this problem, most invert emulsions have an antibacterial additive. However, over time, the additive can wear out. With the right temperature, enough bacteria can grow to plug small valve passages and even block filters. Most of the time, bacteria problems are pretty easy to detect. They usually show up first as a slime coating on inlet filters. Bacterial growth also produces a characteristically bad smell. You'll have to clean and flush the system and replace the emulsion to get rid of the bacteria. Another type of water-based fire-resistant fluid is water glycol. It's made from a mixture of about 40% water and 60% glycol, a chemical similar to automobile antifreeze. Water glycol fluids have some advantages over emulsions. They can be used at much lower temperatures without freezing or separating. And water glycol fluids are more fire-resistant than emulsions. But water glycol fluids don't lubricate as well as petroleum oils, and they tend to cost more. A common disadvantage of all water-based fluids is their tendency to lose water through evaporation. That's why most water-based fluids are recommended for use at temperatures below 140 degrees Fahrenheit. 120 degrees is the most common recommended maximum. Water evaporation from these fluids can cause several problems. Water vapor escaping from the fluid can condense on unprotected metal surfaces, causing rust. Eventually, particles of rust will flake off and contaminate the entire system. Many water-based fluids contain rust inhibitors, but over time, rust will occur anyhow. Evaporation also reduces the fire resistance of the fluid, since less water is available in the fluid. The loss of water also affects the viscosity of a water-based fluid. When using water-based fluids, it's a good idea to have the viscosity checked by a lab periodically to make sure the system is being properly protected. Replacing lost water in an emulsion is not recommended. Without special equipment, it is difficult to get the two substances to emulsify correctly and obtain the proper percentages of each. However, water can be replaced in water glycol solutions. But be careful where you get the replacement water. Common tap water can contain chemicals and solids that can damage a system. If you have to add water to a water glycol fluid, make certain you use distilled or deionized water. The last category of fluids we need to discuss are the synthetic fluids. These man-made solutions operate at higher pressures and higher temperatures. They provide better lubricity and in many instances are more fire-resistant than emulsions. They do, however, cost more than most water-based fluids. One common synthetic fluid is phosphate ester. It is often used in high-pressure systems where fire resistance is needed. If you plan to use a synthetic fluid, you need to make sure your system is compatible with the specific fluid you intend to use. This will save you downtime later on. For instance, phosphate ester and phosphate ester blends are not compatible with Buna-N, a material frequently used to make seals in hydraulic systems. Phosphate esters and other synthetic fluids can also dissolve petroleum-based paints and varnishes used as protective coatings in a system. In addition, synthetic fluids, like water-based fluids, have a tendency to retain air bubbles and to foam much more than petroleum fluids. To reduce this problem, most systems using fire-resistant fluids have large reservoirs to allow plenty of time for air to escape from the fluid. Synthetic fluids and water-based fluids also tend to trap and hold dirt longer than petroleum fluids. Good filtration and the use of magnets can help reduce fluid contamination. Now, we've discussed the advantages and disadvantages of various types of fluids and their properties. Let's take a look at a few important guidelines you need to follow when bringing any hydraulic fluid into your plant. First of all, whenever possible, hydraulic fluid should be stored in a clean, dry place. If you have to store them outside, make sure the drums are turned on their sides so rainwater cannot collect on the top and be pulled in past the seal by changes in atmospheric pressure and in temperature. When transferring from drum to drum or from drum to reservoir, always wipe off the top before breaking the seal. Make sure you use clean transfer pumps, funnels, and hoses. And check your hands before getting near the fluid. You should always filter any fluid added to the reservoir. Dirty hydraulic fluid can plug up many kinds of control valves. It can cause moving parts to stick and wear excessively, and it can act as a catalyst for oxidation. Inspect your system's fluid frequently for contamination and keep any filters serviced regularly. If the filter is being bypassed, it needs to be cleaned or replaced. One final note of caution: make sure you're using the right fluid when changing or adding fluid to a system. Because different additives may have been used, different brands of fluid may not be interchangeable. This concludes our lesson on hydraulic fluids. In the next lesson, we'll take a close look at what happens at the inlet or suction side of a pump.